In this lecture, let us discuss the properties of discrete time Fourier transform. So before that, let us assume the signal g of n gives rise to, or g of n has the Fourier transform capital G of e to the j omega, and h of n has the Fourier transform, I mean discrete time Fourier transform h of e to the j omega. Now the first property is linearity. Okay, so the linearity says alpha times g of n plus beta times h of n gives rise to alpha times the Fourier transform of g of n, that is capital G of e to the j omega, plus beta times the Fourier transform of h of n, which is capital H of e to the j omega. And the second property is time shift. So shift in the time delay by n naught samples, then its corresponding Fourier transform is e to the minus j omega n suffix 0 times g of e to the j omega. And the third property is frequency shift. So that is e to the j omega naught n multiplied by g of n has Fourier transform of g of e to the j times omega minus omega naught. And the fourth property is differentiation. So n times g of n gives rise to j times, you differentiate 1 times the DTFT of g of omega, g of n divided by d omega. So this is straight away you can prove it. Okay, so what is the definition for the discrete time Fourier transform? This is summation of g of n multiplied by e to the minus j omega n. Okay, the limit is from minus infinity to plus infinity. Now differentiate with respect to omega. So d by d omega of g of e to the j omega is equal to, here you can bring this differentiation inside the summation because summation is with respect to n. So maybe I can write one more step, d by d omega of summation of g of n e to the minus j omega n, where the limit is n is equal to minus infinity to plus infinity. So you can bring this differentiation inside. This g of n is constant as far as this differentiation is concerned. So summation of g of n d by d omega of e to the minus j omega n. The limit is minus infinity to plus infinity. Now this is summation of g of n, then it is minus j n times e to the minus j omega n, and the limit is from minus infinity to plus infinity. Now if you rearrange this minus j you can bring to the left hand side, so this becomes I can write now if you simplify, j times d by d omega of g of e to the j omega, this is equal to summation of n times g of n e to the minus j omega n. Okay, if this j comes to the left hand side, then it becomes 1 by minus j. If it comes to the numerator, then it becomes j. That's what I have done here. Now the left hand side I have this term, the right hand side, look at this quantity. Okay, so this left hand side clearly shows that the left hand side is the DTFT of this sequence. See, in the definition, this is the definition. Okay, so g of e to the j omega is the DTFT of g of n. Now in the final expression, instead of g of n, I have one more extra term n here. Therefore, this left hand side, j times d by d omega of g of e to the j omega is the DTFT of what? N times g of n. Okay, so similarly all other properties follow simply from definition. Therefore, n times g of n has the DTFT of j times d by d omega of g of e to the j omega. So I suggest that you carry out this exercise carefully for other properties also. Now let's take an example. So x of n is equal to n times alpha n u of n plus 2. Now how do you find the DTFT of this? If you go by formula, your conventional formula, x of e to the j omega summation of x of n times e to the minus j omega n, this is not as easy as you can do using properties. Okay, so if you use this formula, then it will be difficult to find out. You can, but it is time consuming process. So instead of that, you can use the properties. Straight away you can use the properties and you can find the result. Okay, now how does the given sequence differ from the formula? See, we know the standard formula. Previously we got we got the DTFT of alpha times n u of n, which is 1 divided by 1 minus alpha times e to the minus j omega. Now you can ask me a question, how does the given this equation differ from this? Okay, so in the given equation, in the given problem, I have n times alpha to the n. So I can use differentiation property. Right? If it is n times alpha to the n u of n, no problem. Straight away you can use the differentiation property. But instead of u of n, in the given problem, you have u of n plus 2. That is a thing. So there are just 2 additional samples. Therefore, n times alpha to the n u of n plus 1 has 2 additional terms. Okay, what are those additional terms? One term is sitting at n is equal to, is it 2 or 1? 2, right? This is 2. N is equal to 2 and 1 is sitting at n is equal to minus 1. These 2 terms are additional terms. Therefore, this x of n I can write as follows. Substitute n is equal to 2, then you will get 2 times alpha minus 2. Okay, minus 2 times alpha to the minus 2 u of 0. Okay, so if you substitute n is equal to minus 2, then you will get u of 0. Then substitute n is equal to minus 1. Minus 1 times alpha to the minus 1 u of minus 1 plus 2, it becomes u of 1. And then you write n times alpha to the n u of n. You are going to account from n is equal to 0 onwards. These 2 terms you are separating from this guy. So therefore x of n is equal to minus 1 second. N times alpha to the n u of n plus 2, which is the same as minus 2 times alpha to the minus 2, u of 0 is anyway 1, plus, not plus, minus, this minus alpha to the minus 1 plus n times alpha to the n u of n. I can write like this. Now you can take the Fourier transform very easily. Okay, now you take the discrete time Fourier transform term by term. Therefore x of e to the j omega is, now you can apply the formula, n is equal to minus infinity to plus infinity x of n e to the minus j omega n. Now in this summation I have the term at n is equal to see, this is at n is equal to minus 2, right, and this one is n is equal to minus 1, right. Therefore so I'm not supposed to write like this. Anyway, as far as understanding is concerned, this is okay. This guy is sitting at n is equal to minus 2 and this one is sitting at n is equal to minus 1. Therefore in this summation you have two terms, one is at n is equal to minus 2, therefore x of minus 2 e to the j2 omega plus x of minus 1 e to the j3 omega plus summation of n is equal to 0 to infinity. I can write the rest of the terms, x of n e to the j omega n. Now what is x of minus 2? This term, x of minus 2 is minus 2 times alpha to the minus 2 e to the j2 omega, right. What is x of minus 1? This term, okay. So this is my x of minus 1. So minus alpha to the minus 1 e to the, why did I put 3 here? I am sorry, this is 1, I am very sorry, omega e to the omega plus summation of n is equal to 0 to infinity. What is x of n here? This one in this range, n times alpha to the n u of n e to the j omega n. Now here you can apply the differentiation property. We know the formula, we know the discrete time Fourier transform of alpha to the n. If you multiply by n, then you apply differentiation property. Therefore this is minus 2 alpha to the minus 2 e to the j2 omega minus alpha to the minus 1 e to the j omega plus j times d by d omega of the Fourier transform of alpha times u of n, that is 1 by 1 minus e to the minus j omega. That's it. So for a given problem you must first understand the problem, and that's why I always advise that confronted with a situation, try to understand what the situation is. Okay, this is true not only in solving the problem but also useful in life also. In general, confronted with a problem, try to understand what the problem is. If you understand the problem, half of it is solved, the rest is pure algebra. Okay, so if you differentiate this, then 2 times alpha to the minus 2 e to the j2 omega minus alpha to the minus 1 e to the j omega, then plus alpha times e to the minus j omega divided by 1 minus alpha e to the minus j omega whole squared. That's it. So that's how one has to calculate the discrete time Fourier transform of a given problem by using or by invoking the properties instead of straight away solving the problem. Okay. Now let's continue the properties. The next property is that of convolution. So what is the last property number? Yeah, 4. So the next property number is 5. 5. The fifth property is convolution. Convolution in time. So why did I put a time here? Because we have convolution, the frequency. That's why I specifically put this qualifier time. So convolution time says you take two sequences g of n and h of n, convolve with each other, and then in the frequency domain, this is simply the multiplication. G of e to the j omega, h of e to the j omega. So this is very, very important property, and one of the important advantage that you gain by going to the frequency domain. Okay, this multiplication provides a great simplification. Okay, working out the convolution in the time domain, as you have realized, is not a very simple matter. This is very, very complex in the time domain. But the moment you move on to frequency domain, if you know the DTFT, discrete time Fourier transform of g of n and discrete time Fourier transform of h of n, then you simply multiply and that will give you the convolution. Therefore, if you want to find out y of n, which is equal to g of n times h of n, for example, you have a system, the system has impulse response h of n, and the input is g of n and the output is y of n. This y of n is g of n convolved with the h of n. So instead of doing this convolution in the time domain, what you do is you find the discrete time Fourier transform of both g of n, and you find the discrete time Fourier transform of h of n, which is h of e to the j omega, multiply these two guys, and then take inverse discrete time Fourier transform, you will get a y of n. That's all, and you will get the result. Very simple operation. Okay, so g of n convolved with h of n will be equal to the multiplication of its corresponding discrete time Fourier transform, and then find the inverse discrete time Fourier transform. And that inversion may not require evaluation of an integral. If you look at very closely, like a jeweler who looks at a given ornament, first he looks at with his small microscope, that is the magnifying glass. Similarly, if you look at with a magnifying glass, you may not require to do the integration to find the inverse discrete time Fourier transform. Okay, if you have the properties, then you can easily manage and you can bring back to time domain. Okay, then let us look at the property known as modulation property. So this is fifth property. This also you can prove easily. Modulation or complex modulation. No, it is not complex modulation, complex convolution. I am sorry. Why is it complex convolution? I will tell you. Because now you are going to do the convolution in the frequency domain. So in the frequency domain, the expressions are in the complex form. So that is why this is called a complex convolution. So this property says that two sequences are multiplied in the time domain. So instead of convolution in the time domain, you are going to multiply the two sequences g of n multiplied with h of n. Okay, I mean in the previous case, if you look at here, we had a convolution operation in the time domain. They are one to one, right? So this is a dual. So in the time domain, you have convolution. In the frequency domain, multiplication. Now the dual of this is multiplication in the time domain. Multiplication in the time domain. So in the frequency domain, this becomes convolution. Okay, so g of e to the j omega convolved with the h of e to the j omega. Then this is convolution. Simply you can call by convolution, right? Then why are we calling complex convolution? Because this g of e to the j omega is complex, h of e to the j omega is complex, and convolution is happening between two complex quantity. That is why this is called a complex convolution. This is called a complex convolution. Okay, convolution of two complex quantity. Convolution of two complex quantity. So this is property number 6. Then let us look at 7. Finally, discrete time Fourier transform also gives an easy way of calculating energy of a sequence, and this is given by the so-called Parseval relation. Parseval's relation. See, you can calculate the energy either in the time domain or in the frequency domain. Sometimes calculating energy in the time domain is easy, sometimes calculating energy in the frequency domain is easy, but either way you can calculate it, it doesn't matter. Okay, now let me state the general Parseval's relation. The general Parseval's relation says that g of n multiplied by complex conjugate of h of n, the limit is from minus infinity to plus infinity, is equal to 1 by 2 pi integral of the discrete time Fourier transform of g of n multiplied with complex conjugate of h of e to the j omega and d omega, and the limit is of course in the principal domain minus pi to plus pi, and this one is this relation is called the generalized Parseval's relation, where obviously we have assumed that both g of n and h of n can be complex. H of n can be complex, g of n also can be complex, need not be real. If it is real, then no issues, okay, no need to take this conjugate operation. Now there is a special case. What is a special case? When you take g of n is equal to h of n, then what is going to happen? Then this relation becomes, when g of n is equal to h of n, then you have g of n, then h of n becomes g star of n. In the right hand side, 1 over 2 pi integral of g of e to the j omega, then g complex conjugate of e to the j omega, then d omega. Now the limit is minus infinity to plus infinity. Here the integral limit is minus pi to plus pi. Now this is, you can write mod square, summation of g of n, take modulus and square it, which is equal to 1 over 2 pi integral of g of e to the j omega, take modulus and square it, and d omega, and the limit is minus pi to plus pi. So what is this? Right, the left hand side is the energy in the time domain. This is a energy formula, right? Energy in the time domain. What about the right hand side? The right hand side is the energy in the frequency domain. So the two energies must be the same, because why the two energies must be same, must be equal? Because DTFT is 1-to-1 transformation. 1-to-1 transformation. If it is 1-to-1 transformation, then either you calculate in the time domain or in the frequency domain, it doesn't matter, both must be equal. Okay, no property will be destroyed by taking from the n domain let me write down, this is very important property. No properties no properties of DTFT can be destroyed by taking from the n domain. N domain means what? Time domain. Time domain to the omega domain. Omega domain means frequency domain. It's a very important point. Either you do in the time domain or in the frequency domain, you must get the same result. Let me take one more property and then conclude this lecture. So what is this property number 7? So the next property is symmetry relation. Is it 8? Yeah. Yes, 8. Symmetry relation. This property also I strongly urge you to prove each of them. The proof is very simple, okay? Particularly in the first two cases. It may not be that much difficult. Now x of n has the discrete time Fourier transform of x of e to the j omega. Then x of minus n has the discrete time Fourier transform of x of e to the minus j omega. Let's say this is 1 and is 2. It's very easy to prove. Is it obvious? Yes. You simply write down the definition and you'll get this result. Like what can I say? Discrete time Fourier transform of x of n is equal to summation of x of n e to the minus j omega n. Now let us find out discrete time Fourier transform of x of minus n. So this is going to be summation of x of minus n e to the minus j omega n. Don't put here minus n, okay? No, don't put that. So only you write down here. This is by definition. Okay. Where n is equal to minus infinity to plus infinity. Here also minus infinity to plus infinity. Now you substitute minus n is equal to r in the above expression. So this is going to be x of r e to the j omega r, and here r is equal to plus infinity to minus infinity. So this again once again you can write r is equal to minus infinity to plus infinity x of r. This you can write e to the minus j minus omega r, like that you can write. After all, this r is a dummy variable, this r also dummy variable, this is dummy variable. Now by definition, if you look at here, if you have omega, then you will write it as x of e to the j omega, right? Now instead of omega I have minus omega here, therefore this is nothing but x of e to the minus j omega. Therefore the discrete time Fourier transform of x of minus n is equal to x of e to the minus j omega. It's a very simple proof. In case if x of n is a complex quantity, if x of n is real, no problem. If x of n is complex, then what is going to happen? So in that case, you don't take x of minus n, you take conjugate of that. X conjugate of n has discrete time Fourier transform of conjugate plus you have additionally you have one more term minus here, x conjugate of e to the minus j omega. Okay, and this property also not difficult to prove. Not difficult to prove. Okay, as I said, x of n is complex, then it has real part of x of n plus imaginary part of x of n, j times I of n. Now the question is, what is the Fourier transform of discrete time Fourier transform of real part of x of n? What is the discrete time Fourier transform of imaginary part of x of n? How can you do that? This is also very easy to prove. How do you find out real part of x of n? Real part of x of n is x of n plus x conjugate of n divided by 2, right? Suppose you have a complex number a plus ib. What is the real part? A. How do you get a? Let's say this is z. Then z star is equal to a minus ib. How can I get a? A is nothing but z plus z complex conjugate divided by 2, right? So a plus ib plus a minus ib whole divided by 2. ib will get cancelled. 2a by 2, 2 will get cancelled. You will get a. So you got it here. Therefore, the real part is obtained by z plus z conjugate divided by 2. Similarly, here also, how do you get the real part of x of n? X of n plus x conjugate of n divided by 2. Now you apply DTFT on both sides. Right? So, if you apply DTFT on both sides, then this becomes, what about the right hand side? Right hand side is going to be, what is the DTFT of x of n? X of e to the j omega. What is the DTFT of x conjugate of n? X conjugate of e to the minus j omega, and then this is a scaling factor as it is. The left hand side you have real part of x of n. So therefore the discrete time Fourier transform of real part of x of n is equal to x of e to the j omega plus x conjugate of e to the minus j omega whole divided by 2. By the same token, you can find out j times imaginary part of x of n has the discrete time Fourier transform of 1 by 2 x of e to the j omega minus capital X conjugate of e to the minus j omega. That's it. If you take this j to the right hand side, imaginary part of x of n is equal to 1 by 2j x of e to the j omega minus x conjugate of e to the minus j omega. So one of the things that people often make a mistake is, suppose we have required to find out the DTFT of imaginary part of x of n. Okay, see this x of n is a real quantity. So what you have to do is you have to take j to the right hand side. So that is why I brought here. Okay, so imaginary part, unfortunately the nomenclature is such, it is called imaginary part, but imaginary part is also a real quantity. Suppose if I write a plus ib, this b is a real part, real number. Okay, but the moment you multiply by j or I, then it becomes imaginary. Okay, I think this is where I should stop. So the next lecture from this point onwards we will continue. So let me stop at this point. Thank you.